All right, our next presenter is Mark Goddard from Stack HPC.
Okay, hello everyone. I'm Senior Technical Lead at Stack HPC. My day job normally is working with OpenStack, helping to maintain, deploy, and use it. But this project was a little different, so I'm going to talk today about active object storage. I'd like to thank Stig Telfer for introducing Stack HPC, so I don't have to today. So this is really a talk in two parts. The first chunk of it is going to be a whole lot of context. A lot of it was certainly new to me in the beginning. Probably not all new to all of you, but hopefully interesting nonetheless. And then the last part will be about the work that we were involved in, active object storage, and in particular the reductionist server software. There are various people involved in this project. In particular, I'd like to thank Brian Lawrence, the PI, who provided a number of diagrams and images for this presentation. So first up, disclaimer, I'm not a climate scientist. If I get anything wrong, inaccurate, or omit anything, I apologise. The Excalibur project is it's a program that's trying to improve various research codes to bring them into line with more modern and future exascale systems. So quite often that means porting to GPUs in a performant way. This project isn't that. This is Excalidata. It's one of many projects in Excalibur, and it's focusing on the I/O and storage subsystem. And we're looking at this workflow where we have a large amount of data coming in, some simulation, working with that data, generating an even larger amount of data out, performing some analysis on that data, and then storing the results. And in particular, we're looking at the analysis piece in Excaliwork, which is one of two projects within Excalidata. So Excalidata is looking at active storage servers and software. What's the problem we're trying to address? Well, in climate science, there's an increasing amount of data that we need to work with. I say we, they, I'm not a climate scientist. And that data might be located away from where you're doing the computation. Might be located in a separate storage cluster across a campus network, or perhaps across a wide area network in an object store. So getting that data from the storage system to the compute nodes is pretty expensive. And there are various ways of thinking about that expense. You might think of it in terms of the CPU cycles that get burnt moving it, or the time taken waiting to wait for it to arrive, or perhaps the network bandwidth that's consumed, or perhaps the fact that you need to over-provision the network for these, these large flows that need to arrive, but also the energy that you consume to move the data to the compute nodes. So what is active storage? Well, if we think about modern storage systems, they typically come with a large amount of compute resources. It's useful for things like error correction and working out where each piece of data needs to go. But it's sized for peak capacity, peak requirements, and a lot of the time it's underused. So can we do anything useful with it? To take an example, at Jasmine, the Quobyte storage system in 2021 had 40 petabytes of useful data and 131 compute nodes, which is a sizable compute cluster. Quite a lot of compute capacity there. So people have been talking for a fair while now about moving the compute to the data, and it's termed computational storage, or we're going to call it active storage here. How do we actually do that though? Previously, people have talked about using functions, things like Lambda functions, to package up an application or a VM or a container. Taking my application code, moving it in a portable way to the storage system. But in that more privileged environment, how do I know it's not going to do something bad to the data or the storage system? And how do I take those application pieces and build them into a larger workflow? Well, we're looking at a fairly specific proposed solution in the Excaliwork project, where we take a Dask graph and the idea of numerical reductions to implement this in a particular use case. So the main important thing about a reduction is that the result of the reduction is much, much smaller than the data that it calculates, that it works on. And examples here are minimum, maximum, mean and sum, and in this case the result was a scalar. So climate forecasting is looking at predicting changes in weather averages or climate over, could be a medium term or much longer term, over tens or hundreds of years. And to do this, climate forecasters are using increasingly complex models which try to model more and more of the Earth's systems to predict the accuracy to improve the accuracy of their predictions. Another important factor is that the spatial resolution of the models is increasing. So in 2000, the resolution was, say, 300 kilometers. More recently, in 2017, we're down to 6 kilometers. And they are aiming for 1 kilometer resolution. And a typical data set at that resolution might consume a petabyte. So it's pretty big data they're dealing with. And each time you double the resolution, you're looking at an order of 10 magnitude increase in the compute power and data required. One thing you do get from climate forecasting is some pretty pictures. And if you try not to think too much about what they mean, then they're quite enjoyable. Something that we need to understand is multidimensional arrays, matrices, and the common field that we work with is the average temperature. So in the example here, we've got two spatial dimensions, x and y, and a temporal dimension, t. And this is quite a small matrix, of course, but how would we take this matrix and serialize it onto disk? Well, how that's typically done is to split it into storage chunks. So take a subset of the data, store it on the disk, and then take another storage chunk and store that. The question then becomes, how do you split this array into those chunks? How do you chunk it? If you look at the numbering pattern here, we're increasing along the x-axis, and then the y, and then t. And that's probably the simplest way you might chunk it. But how does the chunking algorithm affect the retrieval performance of different types of hyperslabs? So a hyperslab is a subset in each direction of this matrix. So the subset in blue, for example, is one hyperslab. If we use the pattern that we had here, so x, y, then t, then that is it's efficient if you want to read all of x and y for a given time. But it's very inefficient if you want to read a subset of x and y for a sequence of times. So what's typically done is to chunk the data across partial x, y, and t. So in this example, we might chunk the blue hyperslab and store that in one sequence and then move on to the yellow one. Well, if you look at the numbers, we'll actually move on to 13 to 13, 16, 17, 18, etc. And what this does is it gives you a better performance for reading an average query. Probably not ideal performance for any query, but it's a good average level of performance. So what other things do we have to consider with multidimensional array data? Well, it can have different types. So it could be floating point or signed integer, different precision. Sometimes you get missing data. Perhaps the sensor wasn't working at a particular time, or perhaps some area of the array just doesn't make sense for that data set. How do you describe that? Well, sometimes you can use a sentinel value, a particular number that represents missing data, or a range of data that is valid for the data to take. And anything outside that is treated as invalid. The data might be compressed to reduce the amount of storage required, and it might have a different byte order to that of the compute node. There are various different file formats used to store this data, such as netcdf, HDF5, and ZAR. In the climate community, netcdf is the most popular. It allows you to store multiple variables or arrays in a single file, along with dimensions for those arrays and metadata about the variables. There is a set of conventions, the CF conventions, that define standard metadata for use in the climate community about netcdf datasets. There is a library called CF-Python that implements this CF data model, and it gives you an API to do reading, writing of the data, and also to perform numerical calculations using Dask. What is Dask? It's a parallel computing library written in Python. It allows you to split a problem into separate computational chunks. It will build up a task graph and then map those tasks to worker nodes. And the key thing here is that the computational chunks might not necessarily map to the storage chunks that we just mentioned. So each computational chunk might map to multiple storage chunks or partial chunks. As an example, say we want to take the mean of a variable. Dask might partition our variable space into 4 computational chunks. Each of those would get scheduled as a task onto the Dask compute cluster. And then the mean chunk process would calculate the partial mean of that chunk. To do that, it needs to read all the data from the storage system to the compute node, calculate the mean, and return it to the main aggregate process. So this is where active object storage might come in. So the idea is that we're going to take this Dask graph, and in place of reading the data and performing the reduction, we want to hook in and offload the computation to some active storage system. Now, a key part of this is the PyActive storage library, which was written for the Excaliwork project by the NCAS team. It gives you an NPy-like array interface and allows you to perform basic reductions on the data. And it knows how to break the variable down into the storage chunks and iterate over them, and on each chunk call out to an active storage service. So on the right, we've got our basic example of creating an active class, saying that we want to perform a mean on it, and then subscripting that array with a slice over 2 dimensions. Now, the active class knows that we want to read from a particular netcdf file and a particular variable within the file. Now, I keep saying offload. Where are we going to offload this to? Well, we've got 2 implementations in the Excaliwork project. The first is reductionist, and that's what I'm going to talk about today. And we might have 1 or more servers deployed near to an S3 compatible object store. The second is using the DDN read file system, and they built an extension that runs on their storage nodes that can perform reductions in the same way. So reductionist is a web service that gives you an API to perform reductions on numerical data stored in an S3 compatible object store. There's documentation and code available if you're interested. So to put a few of the pieces together, on the left we've got the compute cluster, and on the right we've got the storage cluster with some pipe of limited size between them. We have the CF-Python library that the user is using to perform some calculation, which calls out to the Dask scheduler and schedules jobs over a number of workers. Crucially, we've got the PyActive storage library installed alongside each Dask worker that implements the hook to replace the read and mean calculation with a call out to the reductionist API. So each of these mean chunks might result in multiple API requests to Reductionist, and each API request to Reductionist will result in a call to S3 to download a subset of the object using a range get from the S3 store. And the files in the S3 object store are netcdf files. We've got a bunch of different features in Reductionist. Apart from the standard numerical reductions I mentioned, you can operate on a subset of an array, a slice or a selection. It knows various different types of ways to describe missing data. It knows how to decompress data in zlib and gzip formats and reverse a byte shuffle filter. If it was stored using a different endianness, then it can reverse that. It's got some basic server resource management, so it will try to limit the amount of CPU resource and memory that is consumed, as well as the number of open files, so that it doesn't crash the server effectively if you overload it with requests. We've got some instrumentation using Prometheus exporters and Jaeger distributed tracing, and an Ansible-based containerized deployment mechanism. So what does the API look like? Well, you make an HTTP post request to the operations endpoint. You need to pass it a header with basic auth containing your S3 credentials. And the payload is a JSON blob that tells you which object in which object store, the data type of the object, the byte order of the object, where in the object your storage chunk is, the offset and the size, the shape or the dimensions of the array, whether it's stored in C or Fortran order, the selection or slice of the array that you're interested in, whether it's compressed, filtered, or whether there's any missing data. And the result that comes back is a byte stream that describes the result. In this case, it's a scalar, so it's just 4 bytes of an int32. And there are some headers that tell you how to construct an array or scalar from that result. The architecture is fairly simple. It's a web server with one request handler, one processing pipeline, which implements a linear sequence of steps. There's no persistent state involved, which often complicates things. And the only external service that we're interacting with is an object store. So this is nice. It's conceptually simple, but of course the devil's in the details of performance tuning and concurrency. The request flow looks like this. The web server accepts a connection, determines which handler to pass it to. We then validate and deserialize the request data to work out what it is we've been asked to do. We go out to the S3 compute store, the S3 object store, download the data, decompress it if necessary, reverse a byte filter if necessary, and perform the numerical operation. Zooming into that operation, this is a sum, but it's quite similar for the other operations. We need to take our byte stream and apply some our type and dimensionality to it. Apply a selection or a view in NumPy terminology to it. And if missing data is specified, we need to calculate the sum over the non-missing elements, as well as a count. If there's no missing data, it's a lot easier, and we can do a much faster sum over the entire array. Once we've got the result, we convert it to a byte array and return. We wrote this project in Rust. Why did we do that? Well, it's a language that's rapidly gaining in popularity. It gives you some things that might sound familiar from C++, high-level abstractions with a low runtime overhead. But what it also gives you is memory safety, which is quite important, and something that I quite like, which is a modern toolchain. So if you're familiar with Python and other languages like that, then the Crates ecosystem will feel quite familiar to you. Would I recommend it? For certain applications, yes. If you need performance and memory safety, it's fantastic. If you can get away with Python, then probably no. We're using the Tokyo asynchronous runtime, which does complicate things somewhat, but it does seem pretty performant. there's an interesting interplay when you have asynchronous tasks like the web server fetching data from S3, and then synchronous tasks like numerical calculation. How do those things work together? You don't want to block the scheduler for any period of time. And another nice thing is that a lot of the code is shared apart from the numerical code to perform each calculation. We tested it in various ways. There's a compliance test suite that tested the original Python Golden model that was built by Matt Pryor. And we do that with a local Minio object store. We've got unit tests, benchmarks, and integration tests with the PyActive storage library. And all of this is run on CI. I'll skip this one. So distributed tracing was quite useful and interesting. We used a program called Jaeger to send traces to. So these allow us to measure the time taken to perform various parts of the calculation. So we've got the entire request span, and then within that we've got the time taken to download the object, reverse compression and filters, and then to perform the numerical calculation. And the interesting thing is that the calculation is by far the smallest piece of the time in terms of wall clock time, and downloading the object is the biggest, although it doesn't actually take that much CPU time. I also use flame graphs, which were quite fun. In particular here, we're looking at the overhead of creating an S3 client per request. And if you look at the blue circles, ellipses, then this time is taken in constructing the S3 client object. After using a shared S3 client, those peaks disappear. So how well does it work? Well, functionally it works. It's fairly well tested and does what it claims to do. But does it perform? I think that really depends on the setup. What is the bandwidth from the compute cluster to the storage cluster, and then the bandwidth from reductionist to the actual storage? What are the compute resources on the compute cluster versus those in reductionist? You can easily create a test setup that shows it working well, but I think we need to see this in production to know how well it works for real workloads. Rust seems to work well. It seems to perform well, although I don't have a direct comparison with C or C++. And there are some issues in PyActive storage with chunk indexing that we need to work out. But I'm told this will be fairly easy to do. Thank you for listening. Got a few minutes for questions.